Um, so we were at the RTL design and functional verification on the front end process. So front end process is, as I was mentioning, that RTL design and um, let me put a pointer so it will be easier for me to highlight. Okay, so RTL design and the functional verification in one of the crucial phase of the chip development cycle, because anything you missed here in terms of not verifying the functionality correctly will cause a bug into the chip development cycle, which actually carry forward all the way through the process. And during the final development cycle, meaning actual product will also carry that bug, right? So that is, and if you identify after the manufacturing that that bug do exist, it actually is a waste of millions of dollars for that particular chip development cycle, right? So that's why RTL design and verification is very crucial. One of the demanding skill set in the industry today. Lots of requirement in this phase around. Okay, so something to keep in mind to explore and see, and I can help you if any one of you are interested to learn more. Please contact me. I'll help you to guide. But this is very crucial phase of the chip design process. Okay. The logic synthesis is nothing but it will convert your RTL design into a gates or the gate level design, which will give you an idea that your design will get converted into how many gates, okay, with respect to what complexity that you are designing. And with that, you get a net list, and you run the gate level simulations to make sure all your, a lot of different functionalities have been taken care, that the gates are all good with respect to the checks are there and things like that. So this is all front end phase of the chip development cycle. Okay, moving to the back end side. Backend is also another, very important process or very important phase in the chip development cycle, because in this phase at high level, I'm not going to go over each and every phases, but at high level, what we are doing here is you are partitioning the design with respect to the architecture, right? Let's say let's take an example of the processor or any other chip like Snapdragon or any mobile SoC processor or mobile SoC chip, right? Which will have a lot of different components in it, right? Graphical process or GPU, central processing unit, cache memory, IO meaning inputs and outputs, some small blocks like USB controller, because you want to also access the USB. There's an HDMI and a lot of different interfaces, right? Then design partition, floor planning, placement, during those phases, what we are doing is we are optimally identifying the blocks which needs to stay closer as a part of the architecture. When I say closer, meaning if two blocks are communicating to each other, more, then we need to make sure that those blocks stays closer to each other. So that way it will consume less power to transfer data between those two blocks, right? Because they're closer, right? It doesn't have to traverse to the long distance, right? So, and if some of the blocks are closer to the input and output of your circuitry, then put those blocks closer to the IO functionality, meaning input and output. That way, that is something we call it as an optimization, right? We intelligently identify those blocks to stay closer. So we optimally partition, optimally floor plan, and place together during this physical design process. Okay, once that is done, there is another process called clock tree synthesis. Here is where different types of clock tree schemes in the industry is very popular and it's available, but depending on the applications of your chip, you choose some of the clock tree schemes. We don't want to go into that detail, but just a high level idea that these are the process or the stages that one needs to go through. Signal routing and timing closure are something where you are making sure that all your timing closure and the design constraints that was received from the fabrication plant. And by the way, I wanted to touch up something that here is when the fabrication or the foundry comes in picture, right? So say for example, during your chip development cycle, we need to identify that which technology node we are going to develop the chip, right? As if you remember, there's a lot of different technology like 65 nanometer, say, 10 nanometer, 7 nanometer, 5 nanometer, something like that, right? Let's say if we have planned to go with 7 nanometer for whatever reason, then we need to tell foundry that give me 7 nanometer related constraint and the timing closure and all of those relevant parameters to us. So those information you receive from foundry and you use it in this development cycle to make sure that those constraints are taken care while you are optimally architecting your physical designing stuff. Okay, so which has a lot of information like metal layer size, the wires, the thin layer, how there's so many thousands and thousands of rules and the checks that they would give you, which we need to make sure that those are all taken care. Okay, and all of these phases has EDA tools, meaning you know design automation tools. So one has to run through those tools and the softwares. Okay, so during this process, after going through all of these stages, eventually it will generate a GDS2 file, which is nothing but a some sort of a binary file, which is a graphical design representation of your architecture or your circuitry, which you have identified or which you have defined in your architecture phase, right? So this GDS2 file will be an input to the foundry or the manufacturing process. Okay, so moving to the next thing now, this GDS2 file will be given to the foundry, and in the fabrication plant, they use this file and they start imprinting the chips on the wafer that we saw earlier in the presentation. Okay, and once those chips are getting manufactured, then next phase is you package them, you test them that all the chips are working nice with certain temperature, this and that, and finally you put it in a box, meaning as an example, we took the smartphone. So once the chip is developed, you put it in a smartphone, you test again to see smartphone is working correctly. You put the message button, it's not actually calling somebody, it actually does the message, right? So the data transfer is going the way it should, right? So that is how you actually make sure there is a lot of testing done before it actually goes into the market. Okay, and then we declare a victory that yes, chip development is done, we are done, celebrate, go into the you know go and enjoy and celebrate the victory, right? So that is the whole process of chip development cycle from start to finish. Okay, so the three key important segment: front end, back end, and fabrication, which is fabrication, test, and assembly. Three main phases of chip design development process, right? Now depending on your interest and stuff, we can choose different category or the phases of this development cycle, and each development cycle you can actually build your career successfully. Okay, um last thing I wanted to also mention this thing, but very important. All of these phases requires EDA tools. This is a design automation tools. So there are three main companies in the world out there. One of them is Synopsys, second is Cadence, third one is Mentor Graphics. Now they call it as a Siemens because Siemens acquired Mentor Graphics. And fortunately, in my career, I got the chance to work with Synopsys and Cadence. So I have worked on a lot of tools on their, with a lot of different cycles here. But these tools helps do a lot of automation and makes things faster. Okay, at high level. Now, now let's understand the ecosystem, right? Whole ecosystem. If you see, I guess we have a few more minutes, right? Right, Sahana? Maybe, I think I'm gonna go a little late, but I guess a student also might have something lined up there in the college. Um, is it okay, Meghna, if I go maybe 10 to 15 more minutes, not more than that? I hope that's fine. Okay, so without waiting, so let's go. Let me give you a high level idea about the ecosystem. So there are five types of primary or the important companies out there. Okay, one is the fabless company, which doesn't have the fabrication plant. Companies who do not have fabrication plant, right? Companies who do have fabrication, meaning either they have fabrication plant, or you know they are only fabrication company, or they have fabrication and design both capabilities, right? One is IDM, which is integrated device manufacturer. One is the OSAT. OSAT is also another type of outsourced semiconductor assembly and testing type of thing, which we saw in the last phase of the chip development cycle. And the one is the EDA, electronic design automation. Now, let me help you understand this, right? So there are, at high level, very high level, forgetting about all of the stages that we discussed, right? There is a chip design, chip fabrication, and assembly. Okay, three main stuff here. Now, how do we correlate this with the ecosystem? So if you see, chip design and chip fabrication capability, whoever has these two capabilities, they are considered to be an IDM, integrated device manufacturer. Some of the companies, like say for example Samsung, Intel, you know these type of companies comes in this umbrella, because they have fabrication plants, and also they are developing their own chips too, designing their chips too, right? So those companies comes in this umbrella. um, Many companies here do not have fabrication plant, but they do develop chip design. Companies like Qualcomm, Nvidia, and a lot of different companies that you see around, they do not have fabrication plant, but they design chips, right? So those companies are called it as a fabless company. Okay. So then the companies who only has fabrication plant but do not have the design capability. Sahana, can you put yourself on mute? I think it looks like I'm echoing. Yeah. So found companies who only has foundry are called as I mean, that goes under the foundry. Companies like TSMC, right? You might have heard about this, TSMC, a company from Taiwan. So they only have foundry. They do not have design capabilities. So those companies considered to be part of, you know, foundry umbrella. And there are OSAT, outsourced semiconductor assembled and testing. There's so many companies out there who just does the, they take the chips, they assemble it, put it together, testing and box building, and make the brand, and just put it in the outside market. All of these companies requires more or less EDA tools from the EDA companies. And as I said just before a couple minutes, there are three main companies in the EDA: Synopsys, Cadence, Mentor Graphics, which is Siemens these days, right? And in addition to EDA, there is always vendor and supplier, right? The service providers, and there are different tool providers and stuff like that. So this is whole ecosystem, right? And being an engineer, we can actually develop our career in one of this umbrella, depending on our interest, right? I choose to be an VLSI engineer as a digital electronics person to jump into a digital design and verification. So I always worked with these type of companies, like fabless companies, like either it could be Qualcomm, Intel, and then different Cadence. I also work with Cadence, Rockwell Collins, and Synopsys, and a lot of different companies, right? In my career. So so it's a choice and the interest. So now that you know ecosystem, you can start stimulating the thought process in your mind to see which excites you more. Okay. And just another thought process, just to give you an thing, think about the iPhone. In a SoC that is being used in the iPhone has a lot of different components like this, right? It has processor, it has a lot of different, CPU, it has touch screen, RAM, meaning, audio controller, because you are also processing the audio, right? There is a GPU, there's so many different components. Now you can correlate what we have talked so far. There are different components talking to each other, as to how somebody would have architected these blocks this way, because there is always optimization and making things possible more optimally, right? So that's why these components are actually closer to the IO, meaning inputs and outputs, because they are actually talking to outside world more often than other components here in between, right? So that's why during the physical design, they identified that these components might be or needs to be closer to IO, right? So these are all, architecture type of a thing, but wanted to give you an pictorial view that when you see an SoC internally, this is what the architecture looks like. And each component here, if I may correlate with the digital design, VHDL or Verilog design, each component has its own Verilog code that somebody would have written during the digital design and the verification cycle, right, to perform certain functionality, right? And now you can actually correlate all of these blocks with the cycle that we just discussed a few minutes ago. Okay, this is how basically any traditional or any type of application specific chips are getting architected and developed and getting manufactured. Okay, so with that, um, this is just an my thought process that there are certain important skill sets for industry today, which is very important that industry is aggressively looking from the engineers like you who would be out in the market in next few months or probably in a year time frame. But have your VLSI digital electronics fundamental clear. If you have not exposed to Verilog or system Verilog type of languages, start explore getting an idea about those languages and fundamentals. There is lots and lots of materials out there online, freely available, which you can just access it. System C and C++. I mean, you don't need all of these languages in detail, but fundamentals needs to be very clear, like polymorphism, object oriented fundamentals. That is very important for any language to understand. Okay. And in your college or somewhere, if you get an opportunity to touch upon some of the EDA tools, just try to put your hands on to understand how the tool works. How do you develop the Verilog code, stimulate it with one particular tool and stuff like that, and debug the problem. Similarly, for physical design and sign off also, there is also a formal verification, which also is another component, very important component as a part of the verification process, and a scripting language for automation. Python is very, very popular these days, but any scripting language you have hands on is really, really value addition in your profile building. Okay, so these are some of the skill sets that I thought I would just give you an idea, so you get more understanding. And with that, I think this is all I had today as a part of the prepared material. But for any question, right? Here is my website. Here is Foundation's website. You can feel free to go there. Our email IDs are here. You can note it down. I'll be happy to stay in touch with you for any questions or anything like that, right? And before I end here, I would like to thank Meghna ma'am and all the professors of PES Engineering College. Of course, audience, excellent audience, sitting in front of me. Very nice, that you have being a very nice audience for last 1.5 hour. So thank you for this opportunity, and thank you everybody. And with that, I don't know if you have a time for questions, but Meghna ma'am or somebody can, coordinate that part. So let me stop my screen share so you will see me on the bigger screen. Okay, how did you? Well, you know what? I know you guys probably might be feeling a little shy, and I was like you guys. When I was in engineering time frame. Yeah, so let me ask a question. I know you guys probably might not. Oh yeah, somebody is.
Hi, sir. Good
Hello.
morning.
Yeah. Good evening.
My question is about how our chip development process is going to change with artificial intelligence.
What is it? Can you repeat? I mean, your voice is echoing a lot.
My question is about how chip development process is going to change with artificial intelligence.
So if I understood your question, how is chip development process is correlating with artificial intelligence? Is that what you want to? Okay,
I,
very good question. You know what? Uh, very good question, because these days whole world is behind artificial intelligence, right? AI is everywhere. So let me give you an example, right? So these days a lot of companies are working on developing a chip which is capable of uh, data processing for artificial intelligence, which means, say for example, you chat GPT or something that you have heard today these days, right? That you ask some question and it will answer you out of the box, right? Like with a lot of information, right? So if you think little bit in detail, like where are those questions, where are those answers coming in front of you, right? There has to be a database, built somewhere, right? And that database has to be processed by something, right? When you are asking a question, your question will transferred into some sort of a digital signal, and it gets the response from the cloud network or cloud database or some database and gives you the answer, right? So all of this process requires the computational processing power, right? So when I say computational processing power is like you need server, and that's where the lot of chips needs to be developed, which can consume this complex artificial intelligent data. It can process and gives you the answer. Okay, so there are a lot of different companies in market like Nvidia and Intel, and a lot of different companies who develops the processor which can handle artificial intelligent capability. So that's where those type of server and the chips and the processor is where you can correlate that how it actually chip development cycle connects with the artificial intelligence. Okay, hope I answered your question.
I
Awesome.
would like to add your details to this answer. Actually, question was how AI is going to change the chip development process. So I
Another.
think EDA
Yep.
tools is
Hmm.
they are accommodating the health facilities, for example, synopsis in SPA and even a place and route. So they are accommodating the AI-enabled algorithms so that the chip design process, the experience, whatever the database has, received, is going to apply for future development.
Very good point. I think I don't know. I don't see the person's face, but I don't know who is talking. But oh yes, hello.
Myself, Dr. Mahesh Puri. I am faculty in the Electronics and Communication Engineering Department here.
Oh, nice, nice
So,
meeting you.
okay,
Very nice,
that was the answer given by me. I
very
hope it
nice.
was.
No, it was a very intelligent and very good thought process, sir. One of the things that I'm working these days, so I work at Intel. You know,
You have to take permission to visit it, I think.
what is it?
I think, can I visit it? That's what
Sure,
I
sure.
want to.
Please, 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 please,
Thank
please.
you. Thank you.
Yeah. So touching upon the artificial intelligence, which you rightly mentioned, right? So all of the EDA tools company these days, and not just EDA, but a lot of semiconductor companies are using artificial intelligence these days, right? To optimize the process, to shorten down the overall chip development cycle, right? Any traditional chip development cycle is like, taking 1 year to multiple year, right? For all the way from start to finish. Now, in this competitive world, everybody is trying to see how fast they can develop their chip and put it in the market, right? And that's where the artificial intelligence comes in picture, through which you can, do a lot of things faster than human, right? By all the data that is available today. And that's where the EDA companies are playing very important role these days. You are right. All the tools like place and route, digital simulation, physical designing, static analysis, formal verification. A lot of tools are putting artificial intelligence together. So very very good, thought process there. This is where this is exactly where the industry is looking this type of skill sets, sir. So I guess yeah, I would motivate all the students to just explore on artificial intelligence side or EDA side, automation side.
One more doubt, sir.
Sure. I'm absolutely fine as long as you guys don't have anything.
It's not doubt, okay? Like, what is the application of avionics in semiconductor?
Very good. Another very good question, which I can answer nicely. Um, so here is what I would say. So let me give you an example. So I myself was working in a company called Rockwell Collins in probably 12 years ago, here in United States, in the Midwest. So one of the project that I was working was for Airbus, aeroplane, the Airbus A350, which is in the air these days. It's functionally, the aeroplane is functionally, it's flying, right? So, so the project that we were working was one of the display device that you remember, on the aeroplane there is a cockpit, right, which pilot uses it to control a lot of digital control mechanism, right? That's where they use a lot of display device, lot of knobs, a lot of control mechanism, lot of data analysis. All those functionalities requires digital chips, right? So the cockpit that we see through which pilot is flying the avionics or the aeroplane, right? So avionics is basically aeroplane and defense related sector.
Thank you.
Most welcome. So I worked on in one of the projects, so I know it's another complex mechanism there.